Hello, everybody. In this set of mini lectures, we are going to talk about electric fields and how those are related to electric forces. In our previous set of mini lectures, we talked about electrostatics, just thinking about the charges on their own and thinking about how charge can be transferred. So in this set of mini lectures, we're going to go just a little bit of a step further than that to wrap up chapter 18 of your textbook. These two images show ways that we can visualize electric fields. Electric fields are invisible, just like magnetic fields, just like gravitational fields. They're all invisible, but we can see how matter and particles interact within this field, and from that we infer the presence of our gravitational, electric, and magnetic fields. So here we have two plates that are oppositely charged. One of these plates has a different charge than the other plate. Maybe one plate is positive and one plate is negative. And all of these sort of black wispy lines here, those are lines of magnetic field between these two plates. So we see that we've got magnetic fields that are kind of parallel to each other inside the plates, and they kind of arch out on the edges of these plates. And here we have electric fields between two oppositely charged objects. And we don't know which one of these has one sign or the other. They must both be opposite charges in order for the loops of these magnetic field lines to connect like this. But we can't tell which one is positive and which one's negative because there's no vector that's given on these field lines. We don't know the direction in which they're pointing, but this image shows that these electric fields exist between these objects, and this is what they might look like. We talked about gravitational fields last semester. We're going to talk about electric and magnetic fields this semester. A field is just a way of conceptualizing. It's a mathematically useful way to conceptualize and map forces that surround any object and that act on other objects at a distance without those objects touching. So our gravitational field that we learned about last semester surrounding the Earth and all other masses represents the gravitational force that would be expected if another mass were placed at a given point within that field. So the field kind of maps out how the forces might behave near a body. The electric field represents the electric force around a charged object that would be experienced if a test charge were placed at a given point. So if you ever hear me talking about a test charge, just imagine a little charge that you place within the field, and then we think about how that little charge might behave within the field. How do we know that an electric field exists? We say an electric field exists at a point, any point in space, if a test charge, anything that has a little particle that has a charge, is placed at that point and it is subjected to an electric force there. A really great way you can think about the electric field is as being the electric force per unit charge at some point in space. We represent the electric field as a capital E. It's a vector, so sometimes we'll put, if it's a vector, we'll put the vector sign above it. Another way you can describe the electric field is the electric field produced by a charge, big Q, on a test charge, little q. Now, let's say we've got our two charges here. We've got charge, big Q. It's sitting at the origin of a coordinate system. It has some charge. Because it has charge, it has an associated electric field. That electric field, because of that charge, is filling up the entire space around it, okay? If I place my little test charge somewhere over here, let's say, that little test charge is going to experience an electric field due to this other charge, big Q. And then the electric field that this little test charge Q feels is the electric force on it between big Q and little q, divided by the little charge here, little q. So the electric field here at point Q, little q, is the electric force between these two charges divided by the charge, this little charge here, Q1. Now we remember that our electric force is Coulomb's constant times Q1 times Q2 divided by the distance between them squared. So if I'm over here at little q, and I need to calculate the electric field at this point, if that's the electric force divided by the charge of little q, I'm going to cancel out my little q on top and bottom. Then the electric field experienced by little q is going to be our Coulomb constant times the charge big Q divided by the distance between them squared. So also we can think about the electric field where this test charge is sitting as being Coulomb constant times the charge on our object sitting at the origin here, divided by the distance squared between where this charge is sitting, big Q, and where we're evaluating the field. Now the units of electric field, big E, are Newton per Coulomb. It's a force per charge. So force is a Newton, charge is Coulomb. So the units of electric field are Newton over Coulomb. They don't have a special name, just Newton per Coulomb. And this is another important piece of information. Our electric field always points away from positive charges and toward negative charges. Technically, how we define the direction of the electric field is that it is the same as the direction of the electric force exerted on a positive test charge. So in this situation up here, we've got our positive test charge, little q. We've got our charge, big Q here, okay? Big Q is creating an electric field. Because these two, big Q and my test charge, little q, have the same sign, they're both positive charges, then the force between them is repulsive. The force between them is repulsive. The electric force due to big Q on little q is going to be pointing away from each other because those forces want to repel each other. So the direction of the electric field in this case would be in the same direction as the electric force here, because we've got our positive test charge Q that we're bringing in toward our original charge that's sitting here, big Q. Let's keep this in mind, that the electric field points away from positive charges and toward negative charges. You're going to answer this question in your concept engagement for this mini lecture. We have a diagram here that shows the electric field surrounding two small charged spheres. Which statement is correct? So the electric field is given by the direction of these arrows here. These are the electric field vectors between our two charged spheres. So based on what we just learned, that the electric field vector points away from positive charges and toward negative charges, which of these possible choices explain what is happening here in the image that you see in front of you? Which of these charges is positive and which of these charges is negative based on the direction of our electric field vectors? Now we're going to solve this problem right here. This is the problem we're going to work on the light board, where we evaluate the electric field at some point away from a positive charge.
Suppose we have a 5.6 nanocoulomb charge located at the origin. So the origin of an XY coordinate system, we place it right where x and y equals 0. What is the magnitude and direction of the electric field at the position x is equal to 2.4 meters, y is equal to 4.2 meters? So here I've written it as a coordinate pair, okay? So what is our electric field, the magnitude and the direction at this point away from my charge? let's think about where we're evaluating this electric field for this charge. We have to go 2.4 meters along the x direction, and then we have to go 4.2 meters along the y direction, not quite straight. Then we're going to be evaluating our electric field at this point right here. I'll just call that point P, and I'm going to go ahead and maybe I'll finish this triangle. I'll go ahead and draw this in right here. And so this makes a right angle for a right angle triangle right here. Right. So the first thing I'm going to think about, maybe before I even do any numerical calculations, is think about the direction of the electric field, or let's at least draw the electric field vector at point P. So for our electric field vectors, the electric field is always drawn away from a positive charge. Since this is a positive charge, then my electric field at point P, due to this positive charge, is going to be directly away from that point, kind of along this line that I could connect between my charge and where I'm evaluating it. This is then going to be the direction of my electric field vector. I have to get its magnitude, and I want to get this angle that this electric field is with respect to the positive x-axis. Now we know which direction it's going to point. Let's go ahead and calculate the magnitude. I'll put bars around it to represent the magnitude. It's going to equal to a Coulomb constant times the absolute value of our charge, big Q here, divided by r squared, where r is this distance from the charge and where I'm evaluating my electric field. Okay. Now, let's go ahead and fill this in. K, our Coulomb constant, is 8.99 times 10 to the 9 Newton meters squared over coulombs squared. And my charge is 5.6 times 10 to the minus 9 coulombs. 1 nanocoulomb is 10 to the minus 9 coulombs. And then I'm going to divide it by the distance squared here. Okay, so what is our distance? Well, we've got two legs of a right angle triangle. To get this distance here, which I'll call r, the distance between Q and where I'm evaluating my field at point P, I can use the Pythagorean theorem in order to get this distance, since I know the legs of these other two legs of my triangle. Remember Pythagorean theorem, r squared is equal to x squared plus y squared. So let's see, I'll put it down here. R squared is equal to x squared plus y squared. So r is going to be the square root of x squared plus y squared. And that's equal to the square root of, I've got my 2.4 meters squared plus my 4.2 meters squared, and that gives me a distance for my value of r here of 4.84 meters. And that's what I'll put here for r, 4.84 meters, and I have to square it. Now, a lot of times students, when they're solving these problems, will forget to square this value right here. So don't forget about that. I see that happen quite often. All right, then with that, we find that the magnitude of our electric field at point P is 2.15 Newton per Coulomb. Okay? The unit for electric field is a Newton per Coulomb. How did I get that unit? Well, let's see. I've got a meter squared here that's going to cancel with this meter squared. And I've got a Coulomb here that's going to cancel with one of these coulombs. And that just leaves me with a unit of a Newton over a Coulomb. So that's my unit for electric field vector, Newton per Coulomb. We're not quite done yet. We've got the magnitude, but we need this direction, this angle with respect to the positive x-axis. Now, we can get this angle by thinking about geometry. Now, here I have a straight line going from my charge Q all the way up along my electric field vector. Okay. And then I've got this line right here. This is essentially parallel with the x-axis. And then I have this other line here parallel with the x-axis. So these are intersecting this line right here. So we've got these angles here and here, which are congruent. They're the same angle, okay? So if I can get this angle right here, which I'll call theta, it's going to be the same as this angle theta up here. My angle theta, I can use, well, I actually know all three of the legs of this triangle now, so I could use sine, cosine, or tangent to get this angle, but I'll just go ahead and use tangent. The tangent of my angle theta is equal to the opposite side, 4.2 meters, divided by my adjacent side, 2.4 meters. So my angle theta is the inverse tangent of, these units cancel, 4.2 over 2.4. And that gives me an angle of 60.3 degrees. So to fully report the electric field here at point P, we would say that the electric field at point P is 2.15 nanocoulombs at an angle of 60.3 degrees from the positive x-axis.